piece of business done. It's my great pleasure to introduce Professor Dieter Fox, who's in the Department of Computer Science and Engineering at University of Washington. He's won every possible best paper award I think that you can win at various points in his career, and he's been editor-in-chief of the most important journals in robotics and machine learning and parts of AI. He's on everybody's advisory board. He runs a very prominent group at NVIDIA whilst holding down a full-time position as professor in computer science department. He's a fellow of ACM, IEEE, AAAI. Most recently, I was delighted to see, Dieter, that you got the Pioneer Award. Congratulations for your 2020 Pioneer Award, well deserved. Yeah, I took the opportunity this morning to look at your Google Scholar, and so Dieter is now, his Google Scholar gives him 117, his H index is 117, so that's quite a feat. My experience of Dieter's work is, of course, talking to him, but also when I read his papers, it's not, I'm afraid many in the last 5 years of robotics, we've gotten so excited by the technology that the field has gotten a little bit away from some of the foundational questions. And what I love about Dieter's work is, in addition to the stuff that he does being very exciting and the systems that his people put out are very, very interesting, I always have the sense when I read his papers that he's got his eye on the foundational questions. He's trying to think about what it was that actually made the thing work, or what it might be that would not make the thing work well. This is unfortunately has become a little bit rare, I find, in these latter days of the field. But Dieter is just a shining example of how to do foundational work at the cutting edge of these very capable technologies that we don't perfectly understand right now. So, okay, Dieter, thank you so much for agreeing to come and talk to us. It's really a pleasure to have you here and introduce you. And I'm just gonna get out of your way and let you give us your exciting topic.
Thank you so much, Dan. First of all, for inviting me. It's always just great to be with you. Of course, now unfortunately not in person, but I'm looking forward firmly. I'm counting on seeing you guys at ICRA next year. So that's planned. That's going to be my first big outing for a conference. So that'll be great. And thanks also for the overly kind introduction. I'll share my screen here. I hope that's working. Quick confirmation.
Yeah, looks good.
Okay, perfect. Yeah, so as Dan said, I'm currently sharing my time between University of Washington and also leading the robotics research team at NVIDIA. And in line with that, actually, I'm going to kind of talk about work, a lot of which was done kind of jointly between actually my lab at the university and NVIDIA itself. Some of you might have seen certain parts of that talk when Arsalan Musavian, one of the research scientists in the lab, gave a talk recently, but I tried to kind of minimize the overlap. Just for context, if you think about robot manipulation, especially object manipulation, right? And I'll mostly today focus just on picking up rigid objects and let's say moving them from one place to another. And there are kind of different ways on which you can approach that problem, right? And when we started the NVIDIA lab a bit more than 4 years ago, we said we'll start out with what we call a model-based approach. And this is very much in line with kind of the, let's call it the more traditional thinking, where you assume you have 3D models of the objects you try to manipulate. You have 3D models of the environment you're operating in. You're trying to explicitly estimate the state of the environment, which in this case would be, where are the objects, where is the manipulator, and then you can do explicit planning for the motion of the manipulator. And with that approach, actually, I think we were able to put together a system that can do a pretty nice manipulation task. So I'll show you here on the left is, for example, the Franca robot putting a sugar box into the cabinet up there. And on the lower part, you see actually it's kind of like the internal state of the robot, where we use a depth camera to track the environment. So we have a model of the kitchen that reasons also about the articulation of the cabinet door. We do post detection, 6D post detection of the objects. Here, the sugar box, the white one, indicated in the lower part. We do this using a combination of color and depth information. And the advantage of, I would say, the model-based approach is that if you have this information, you can do very nice explicit planning and control. Okay, so this works very well. So here the robot can avoid collisions when it's trying to grasp the handle of the door, and now it can close the cabinet. We can also do longer term planning in this area. This is work on the right. You'll see Kalen Garrett did that as an intern with us. He is from Leslie Kalbling's Thomas Lozano Perez lab at MIT. And we're very happy that he joined us not too long ago as a researcher as well in the lab. And that is an area called task and motion planning, which reasons about longer term goals. So imagine you have this scene here on the right, and the task for the robot is it has to find where in this case, I think it's the spam box. It's in one of the two drawers that you can see here in front of the robot, and the task is to find it and put it in the other drawer, right? And we can do the planning and the observation, everything in a fully autonomous mode. So here the robot, it opens the drawer, it closes it, now opens the other one, it can detect the drawer, it can now do the planning on how to pick it up. Again, in this case, we have models for these objects, so we can even pre-store how to pick up the object, and the robot knows that it has to close the upper drawer before it opens the lower one, and now it can put in the object. Okay, so this is the kind of high-level reasoning that these, what I would call model-based approaches, enable. So that is, I think, a really big plus for these systems. Also that they are just very broadly applicable, right? If you put the robot in another kitchen, as long as you have a model, you can just do the same kind of complex reasoning in any of these environments. The big limitation is, of course, that we need models, explicit models in this case, which in some cases might be available, but in many cases are not available. And also what we found out that these systems can be actually surprisingly brittle at times, because when you, for example, want to pick up an object, the robot first estimates the pose of the object in the environment and then reasons about the internal estimate of where the object is. And if that estimate is not accurate enough, or it's just wrong, which can always happen, then somehow the robot won't be able to pick it up. So there's somehow this bottleneck between what the robot perceives and what it's reasoning on. And that bottleneck in this case is just a 6D pose estimate, right? So the robot actually throws away a lot of information that might be in the raw sensor data by going through this bottleneck. And that, in my experience, actually incurs quite some brittleness in these systems. Okay, so in this talk today, I wanna talk about some other efforts that go more in the direction of saying, okay, how can we do reasoning that is what I would say closer to the raw perception of the robot? Okay, and of course, there's a lot of deep learning these days involved in these techniques, which enable that kind of reasoning. There is 3 sections. The first one is something that, again, Arsalan already talked about a lot, which is just how we can grasp and place unknown objects for which we do not have 3D models. And then I'll talk some even more recent work on, one is direction towards kind of learning representations for manipulation that are not as explicit as the 3D shape models. And then also some recent work that involves language for manipulation tasks. Okay, so let me start with the first block. Again, this is work that's very much driven by Arsalan Musavian in the lab and his colleagues also, and several of the interns, where the idea is how can we manipulate objects for which we don't have models. Okay, so let me just contrast that a little bit to the model-based approach that I showed on the first slide. So in the model-based approach, what you do is typically you say, I have an observation, and let's say I want to pick up the water jug, and you have a 3D model of the object. Now what you do is you take the camera information, You do traditional, let's call it pose estimation. Also nowadays, of course, with a lot involved with deep learning, and you're trying to estimate the object's rotation and translation. And then assume that even this object, you have annotated grasps for the object. Okay. And now with this information, what you can do is very easily, you just transform the grasp using the object pose estimate into the robot's reference frame or the camera's reference frame. And now the robot can pick up the object using kind of the model as a surrogate for the input data. In contrast to this, when I say model-free grasping, then what we'd like to do is we have an observation and we go directly from that observation to grasp poses. Okay, so there's no explicit 3D model matching involved in between. How can we do this? Of course, now there's a lot of deep learning involved, and the question is often, where does the training data come from? It turns out that nowadays with good physics simulation, and of course, a lot of excellent tools being developed by the NVIDIA Isaac team, allows you to generate a lot of training data. So imagine here we have, it's again, this red is kind of the spam can, and we just take the object and we randomly sample possible grasp poses around the object. And for each of these grasp poses, we put it in the physics simulator and say, close the gripper, and then we move the gripper and see if the object is stably placed in the hand. You can see this here, that many of the grasp poses, of course, fail, but some of them succeed. And we can do this evaluation nicely in parallel. We can do this on many objects. And then what you get out of this is, for example, for this object model, you get a set of poses that have a high chance of succeeding using the physics simulation. Okay. Now we can generalize that to more objects. We did this here in a acronym paper driven by Clemens Ebner, where we use almost 9,000 objects and feed them all through the simulation engine. And then what you see here on the right is a data set with objects, and all of them are annotated with good grasps. Okay, so these are relative poses of the gripper that have a high chance of resulting in a stable grasp of these objects. Okay, we can now use this to train a deep network that hopefully can learn from this amount of data what makes a grasp succeed. Okay, so it's very, very simple, actually, the idea. And how we do this is the following. We want to train a network that can do that based on the point cloud that you would observe with a depth camera. We don't want to assume that the network has access to a 3D model, because in the real world, we want to be able to do this just based on raw observations. So the input to the network is a point cloud. In this case, it's called a conditional variational autoencoder. We don't need to go into details, but the nice thing is we can train this network to take as input a point cloud and sample as output. We can sample different grasps that have a high chance of succeeding on this object that is represented through this point cloud. And by what I mean is that the sampler is trying to replicate the distribution that was given to it through the training data. Okay, it turns out that the sampling process is not quite precise enough sometimes for actually picking up an object. So we can now train a second network. The grasp evaluator is again a deep network that now takes as input the point cloud of the object and the gripper. And its task is to output what's the probability of this being a good grasp. Okay, you can see here on the right, for example, the upper one might be a good one, the other two might not be good. And since these are deep network, we can actually compute gradients through them, which means we can actually refine these grasps simply by computing the gradient of the error with respect to the pose of the gripper. Okay, so this is the same thing you do during learning. We can also do during inference by propagating the gradients through the network. Okay, so the output now of the system is from a point cloud, we go to a set of grasp poses that have a good chance of succeeding. Okay, and again, all of this is just done by matching the training data. Here are some examples of this actually working pretty well on a table. This is more or less really just out of the box, meaning the system was solidly trained in simulation. We have not seen any real data in the simulation. The object that you see here were not in the training data. So these are unknown objects. And the robot actually has a pretty good high success rate here immediately on these objects. Okay, you can see on the lower right is an example where it's not quite grabbing the mug at the handle. So what you see here is an individual object on the table. We can also extend this now to more cluttered scenes. This is some follow-up work we did, where the input now is, again, an RGBD observation of the scene. The first thing you need to do, even, I think, if you want to not assume object models, I think segmenting a scene is a very basic fundamental capability. So we did some additional work on unknown instance segmentation. So in this case, imagine we can segment the scene into different objects. And then someone might indicate, okay, it's the yellow, the mustard bottle that we want to grasp, which is the segment belonging to object number 3. We can now kind of cut out the yellow object and its vicinity. And then we can just run the grasp generator on the point cloud of the mustard bottle, which is what you can see here. Okay, this is exactly the network that I showed you on the previous slide. And in addition, what we now have to do is we need to check that these grasps are not in collision with other objects in the scene. For that, it turns out using a deep neural network that checks for collisions is better than just doing it using the point cloud itself, because due to occlusions and partial views, the point cloud doesn't capture actually the geometry of the scene as well. So it turns out we can train a network, in this case it's called scene collision net or collision net, that does better at checking collisions with these grasps. And then we can see which of the other objects are mostly contributing to these collisions. And we can now say, oh, well, if I want to pick up the mustard bottle, I first need to get another object out of the way. Okay, how this works now in practice is, here's one example. On the left side, you can see kind of just the external view that's not being used by the robot. On the right side, you see the view from the robot's camera, which is here placed on the gripper. And let's assume the user wants the robot to pick up the white coffee cup. And using the reasoning that I explained, the network determines that all the other objects are actually in collision with the grasp. So the robot could not pick up the coffee cup right now. It can determine that the sugar box on the left, the red one, is the one that is mostly contributing to these collisions. And now we just revert to saying, okay, let's first get the sugar out of the way. So now we feed the same scene into the system and say, this is our target. In this case, there were grasps on the sugar box that were not in collision with other objects. And now the robot can actually go and pick up the sugar box and get it out of the way. And then it just goes back to the scene, reassesses it. And in this case, it can find grasp for the coffee cup and can pick it up. Okay. So why I'm showing you this is, so our ultimate goal here is to say, we have what I showed you initially, these model-based techniques for task and motion planning, which is kind of, if we had perfect observation, which is kind of like a gold standard for what you might be able to do. However, it makes these assumptions about known objects and all of that. How close can we go to the kind of reasoning without assuming object models, right? And what you can see here is that even without assuming any models, we can already do some reasoning that you would typically say requires actually some kind of planning about the scene. Okay, here's some recent work that we also had at Call, just one quick example of the other kind of reasoning you can do now with these systems, again, without any models, as what Chris Paxton did, a project here, where it's about picking up objects and placing them at locations relative to other objects. So in this case, the language input, for example, place the mustard behind the bowl. In this case, it's a red bowl. And you see these three different scenes. And we have a system now that can, for example, first of all, it can pick up the mustard and then find a stable placement for the mustard behind the bowl. And you can see that the different geometry behind the bowl requires the robot actually to reason about different heights and what is good placement positions. Okay. So again, these are things that I would say 4 years ago when we started this, we would have said, you can only do this if you have models, right? And nowadays, with enough training data, we can do this with systems that don't require any object models anymore. One other example of what you can do with these systems is now, for example, handover of unknown objects. So in this case, it's a person handing an object to the robot, and the robot doesn't know what the object is, but it's using the same technique that I described, this grasp neural network that then can kind of reason about how it should approach the object in order to pick it up. Additional complication here was also, for example, we don't want the robot to squeeze the finger of the person. So we need to do some additional segmentation to make sure that we detect where the fingers of the person are and things like that. It turns out, I must admit, handing over objects to a robot is much harder than I initially thought. It's one of those projects where you think, oh yeah, we can do this easily. And then it turns out there's a lot of complicated stuff going on to enable that. And this is still an ongoing project. Okay. So with that, I want to end the first part where, again, the goal was to show how far we can get without any models. And the work so far has been driven very much by, we take a certain capability we want to enable, and now we train a deep network, often based on point cloud reasoning. We train a deep network to achieve that task. Okay, but typically the different networks for different kinds of tasks were all trained specifically for from scratch again, right? And in the next part, I want to talk about very early work towards learning representations that are more general, kind of what we might say as something that that goes beyond a highly specific task, but has more general capabilities. So my dream actually for this is the following. We have seen in, and I'll say that on the next slide, but we've seen a lot of success, especially in computer vision and language processing, where people train very, very large deep neural networks on very large data sets. And these networks are trained on such a variety of data that they can be used on a variety of downstream tasks. So what I would like to achieve ultimately is, can we train neural networks such that any lab that wants to do robot manipulation can download these networks, you feed in your camera data stream, and out comes a representation that is useful for any kind of thing you want to do with the objects in the scene. Okay, so a general representation that hopefully is not just for my lab and that works in my lab, but hopefully works in any lab anywhere. Of course, we're very far from that, but that's where we would like to go. Okay. And this is work that is very much driven by a student at UW Wen Tao and a postdoc, Karthik Desing, who is also on the faculty market this year. So again, the motivation for this is the big success we've seen in computer vision and language processing. You might have heard of models like BERT or OpenAI just did Clip, GPT-3, Megatron, more recently also masked autoencoders. All of these are techniques that are trained, for example, in the vision case on very, very large internet size data sets and trained with relatively weak supervision. There's some kind of supervision that you need to bring in, but extremely weak supervision and outcome models that can be very quickly adapted to downstream tasks. Okay, and I think the kind of architecture that we see coming up over and over again in this context are these transformer networks. And I'll show you a quick example of those in this context. But I feel like we have not seen anything like this in robotics. And of course, us roboticists say it's just because robotics is so much harder, right? And of course, it is so much harder than pure computer vision or language. But I think at least we should look at what can we do in robotics, right? And there are many open questions. For example, what kind of tasks should we use to train these robots? What kind of training data do we even need? How much is necessary? In robotics, I think we often tend to say, I want my robot to learn everything from 10 examples. And I think we might want to look at what happens if we give it millions and millions of examples, right? Maybe it can learn something that is kind of magical, okay? And then also, what kind of supervision can we give to these systems, and from what supervision can they learn these representations, okay? And in this line of work, also the question is, what kind of representations do we want? Do we want just like image in and out comes a big 1,000-dimensional vector that represents that image? Or do we want to have that representation have some kind of structure? And the motivation for this work was that we believe some kind of structure, even in this representation, should be actually useful. And in our case, we would like to have a structure so that at least we can represent objects individually in the scene. So each object is represented by some kind of embedding, okay? So, and this is Spatial Object-Centric Representation Network, SORNet. And here's how it works. So the input should be an image, and you'll see already, apologies. So I gave you this big story, but you will see that we just a tiny step in this direction, right? So it's far from what we want to achieve, but so you'll see it's kind of a very simple block stacking, for example, environment. Okay, so your robot that is kind of stacking these blocks. And again, we would like to achieve a representation that reasons about objects in the scene, because I think that's kind of a fundamental kind of building block for representing scenes. And imagine in the scene you have kind of views or images of objects that you care about in the scene. And these views could be, the user could have taken a picture of the object early on, or if you think about a temporal system, these views could come from earlier parts of the sequence or something like that, right? But for now, let's just assume it's these 4 canonical views of the object. And what we would like to achieve is train a deep network that gives us some kind of representation of these objects. Some in this, I don't even remember how many dimensions, but let's say 100,000 dimensional vector that represents each of these objects, okay? And by representing the objects, I don't mean necessarily the shape or specific geometry, but something that can be useful for manipulation, okay? Now the question is, how can we train that? And we explicitly made the decision not to train this, for example, on giving supervisory data on the 60 pose of objects or something like that, or on the shape model of the object. We wanted to give it a supervision that is less immediate and doesn't constrain these embeddings as much. So in our case, we chose a system that comes from, wait, let me briefly move this here in the screen so I can see better what's on the right side of my screen, is this logical state. From task and motion planning, again, we have learned that reasoning about a scene at a higher level enables, of course, excellent long-term reasoning about the scene, right? And this is kind of how also people might reason about the scene. For example, you might ask a question, does the robot currently hold the green block, right? Or is the yellow block clear, the top of it, or is there another object on it? You might ask, is the blue block stacked on the red block? So these are the kind of things that we give to the network as supervision, which means we want to learn embeddings such that we can answer these kind of questions. Okay, that's the only thing we care about for now. So very simple. How do we do this? Now a bit more specific on the network architecture. So again, this is a transformer network. So first of all, we generate a grid, a subset of a grid for the image. And these are architectures that have been shown to work well for various vision tasks and different models for training large scale. So now we have these patches down there. So the image is represented by a sequence of patches. It turns out for transformers, they are not ordered at this point. And we also feed into the transformer our canonical object views, which means these are the things we care about. Details don't matter at all, but we somehow kind of represent all of these in vector form and matrix form. And we also provide for each of these patches what's called a positional encoding, so that the transformer can actually reason about which of these patches comes from where in the image, for example, right, intuitively. For the object views, we don't provide any positional encodings because we don't want there to be any order on in which order you ask these, you feed in these query views, let's say. And now all of this is fed through standard transformer architecture. You can look at the paper for details. And out come embedding vectors for the 4 query objects. Okay, so I'm not gonna say anything about how this goes internally in the network, but this is pretty reasonably standard transformer architecture. What's new here is that we condition the whole reasoning on these canonical object views on the right side. Okay, and then we use the standard architecture and read out these embedding vectors. So at this point, of course, this is just a representation of this, and there's just no idea how we can learn this. And I want to show you briefly how we can learn this. One nice advantage of this architecture is the following. We can, for example, say, well, I only care about 3 objects in the scene, and the network automatically adjusts to that and generates embeddings for these 3, or we can present these objects in a different order, and the representation is very flexible with respect to that. That is the key reason also why we chose this architecture here, okay? Now, we want to train this, as I said, using high-level logical supervision, not explicit 60 post kind of supervision. So here's a scene, and these are all predicates that our existing task and motion planning system is actually using. So in simulation, we can pretty easily generate those predicates. So for example, things like, is the blue block held by the robot? We have different regions on the table, for example, and then you might ask, is the red block in the far region of the table? We also have some predicates that look at pairs of objects, right? Is the blue block aligned with the yellow? This means if the robot should stack one object on the other one, are they aligned vertically? Okay, but again, these are just kind of logical predicates at that point. Now, how do we use these for training? I want to briefly show you on the next slide. But again, the key highlight here is we don't supervise the training anywhere on providing segmentation masks for the objects or bounding boxes or anything like that, right? The only supervision is really just at the logical level. The training now goes as follows. We have in the lower part here, we have this big transformer network that I showed you. And what we can do now is with these predicates, we have a so-called a set of readout networks. So these are pretty simple multi-layer perceptron networks. It's 2 layers, so very simple. And for each predicate type, that's important, these are typed, we have one of these MLPs. So here, for example, imagine we have an MLP that is responsible for answering the question, has the robot object X in its hand? Okay. The input to this network is the embedding of the object that we care about. So let's say, in this case, I want to query the blue object, which is given by the canonical view. So the predicate gets its input, the embedding of the blue one. And in the training data, we know whether the robot has it or not, or we can say true or false. In the same scene, we can ask it about, okay, Does it have the green object? In this case, for example, it might have the green object. And this is the supervision we are using to train the MLP, which is the readout network. But at the same time, the gradients go all the way through the transformer, and that is also being used to train the transformer at the same time. We also have MLPs that look at pairs of embeddings. For example, there's an MLP that says, is the object X stacked on Y? And the input to this is just a concatenation of the embeddings of these two objects, and outcomes false in this case, for example, right? And in some cases, you might have true as a desired outcome, okay? But again, the key trick is we have this set of MLPs that just serve the purpose of reading information from these embeddings. And you might argue that ultimately we might not even care about the predicates themselves. We are using the predicates to learn embeddings such that they are taught to contain the information that is relevant for these manipulation tasks. Okay. Here's what the training data looks like. And this is all done in Isaac simulation here, where we have, for training, we have 134,000 sequences of the robot. Kind of, it's always in the training, it's always 4 blocks, and the robot is always stacking 4 blocks. We randomize, as you can see, the background, the textures, shading, and all these kind of things. And we have actually 3 camera views. In different settings, we use one of them or all 3. The camera views are also slightly randomized, so it's not a single view, because otherwise we know the deep networks would easily overfit to that. We have about 405 here different colors that we're choosing from. And the supervision comes through these logical predicates that we can generate in simulation, described that on the previous slide. And in testing, we have 10,000 sequences. We're using objects of different colors that were not in the training to make sure that there's, of course, a generalization. In testing, we're looking at scenes that contain 4 to 6 blocks, so different numbers of blocks as well. And also the tasks are slightly different. So there's unstacking, putting different multiple stacks and things like that. Okay. And the first thing now you can ask is, did the network learn to actually answer these predicate questions, right? And I'm not going to go obviously into the details of the numbers here, but the main thing is, first of all, that the network architecture, actually you can see here we are in the around the 90s, around 90 in the F1 score, which means that the network architecture is actually very well suited to answer these predicate questions, okay? Which means, is object A stacked on B, and things like that, or does the gripper hold the red object? What's interesting also is that changing the number of objects, adding objects that are not even being queried in the scenes, and also actually transferring to the real world works very well. So there is not a huge drop in the accuracy. So we can run this on a real robot with a real RGBD camera as well. And the randomization makes it pretty robust to this. Okay. And again, you can look at the details in the paper, and we can use this now, for example, at least for at the planning level about a scene. So here's now the real robot, and we feed into the network an image of the scene. We ask, for example, the query objects down there. These can also come from simulation, so the canonical views don't have to match the scene accurately. And then the network actually generates the predicate description for the scene. Okay, as I just described, this is the SORNet. And then let's assume the robot has a goal, and we can now generate a sequence of actions that goes from the current predicate description of the scene to the goal description of the scene, and we can execute that. A major caveat here is, at this point, the skills, which means the low-level execution of these steps, is still done using a traditional approach. So the SORNet is only helping at the predicate level at this point. Okay, but I'll get a bit more to that on the next slide. But again, we can now use this for some real world kind of planning, even though the system is solidly trained in simulation. Okay, and now comes, from my perspective at least, the most interesting aspect of this work is the following. And the question was that we asked was the following here. We train our network using these logical predicates, right? And the question now is, do these embeddings that we learn contain any kind of spatial information, like metric spatial information about the scene? Okay, because we're just training it on the logical level, maybe it just learns to totally overfit to this logical representation and still has no idea what's actually going on in this 3D notion of the scene. So what we did is the following. We took the trained network and we now try to see, can we train additional MLPs that take these embeddings of the objects and output the relative XYZ position of these objects. Okay, so in this case, the readout objective, so we generate some additional training data, but the training data is not used to change the embeddings. The training data is only used for the readout networks. And what we actually ask is kind of, do the embeddings contain spatial XYZ information, even though they were only trained on the predicates? And it turns out, I wouldn't show you otherwise, I guess, it turns out it does. And we can now use actually these readout networks from the embeddings to guide the gripper to these different objects. So what you see here in these arrows is where we tell the robot, give me the relative pose between the gripper and an object, one of these objects, and we use the relative pose generated by the network to guide the gripper to the object. Okay, so which means we can see that there's some real continuous spatial information in these embeddings, even though they weren't explicitly trained on that. And that's, from my perspective at least, a very exciting first indication that there might be a good chance that we will be able to train, if we go to much larger system, much larger tasks, that we can learn embeddings that actually can be used for continuous control tasks as well, and that generalize to new tasks. Okay. Oh yeah, we also did it on other kinds of objects. So it's not only on little blocks, but we also used the clever data set to show that it works on different kinds of objects with different shapes and sizes. Okay, I'm in the interest of time, I'm going to skip this. Okay, so that was on, again, the general notion of how can we learn embeddings for objects. And now I want to show you one recent piece of work that combines also language and a kind of different representation, again, of a scene for manipulation. And in this case, rather than the object-centric representation that you saw in the previous portion of the talk, here it's what I would call, it's an action-centric representation. And this is something that was very much inspired by some really nice work by Andy Zhang's team on transporter networks. Okay, so the idea here is that for many manipulation tasks, actually, the notion of objects might not even make that much sense, because if you talk about granular media or deformable things, right, then rigid objects clearly don't fit that description anymore, right? So in this work, this is work that was driven by my student Mohit. It's called Clipboard, and the name comes from combining clip with transporter networks. And the idea is we want to teach robots manipulation tasks from a very small number of examples. And again, the key foundational work for this on one side is transporter networks by Andy Zhang. What they did was a really nice representation where you have top-down manipulation tasks, okay? Tabletop kind of setting, you have a top-down view on the scene, and they showed that there's many interesting tasks that you can solidly describe by kind of pick and place, which means where should the gripper go to pick up an object and where should I place the object? You can see here on the right some examples. You can describe even like swiping granular media into a certain region can be described kind of as a pick and place task. Or in industrial settings, it's called kitting, moving objects from an unsorted bin into certain configurations can be described with these tasks. And again, they came up with a very nice network architecture that is well suited for these tasks. And they showed that they can train their networks on very few examples. There is no object models or anything like that needed. There's no pose estimation or segmentation required. The key limitation of that work, though, was that the system had no what we would call, let's say, semantic understanding of what was going on. There was no good generalization, which means for every single task, they had to train a separate network from scratch. Okay, so there was no generalization across tasks, or also the system would not generalize from one color to another color and things like that. Okay, so we wanted to see if we can extend this work to encode some more information about the semantics or language that people would use to describe a scene. Okay, and that now brings the connection to Clip. I don't know whether you have seen this, but Clip, I must say I was blown away when I saw the first results of Clip. Clip is a work that was done by OpenAI, and it's in this line of work of using very, very large data sets with weak supervision and train representations, embeddings for vision data and language data in this case that can be applied to many downstream tasks. How they did this, it's just illustrated here on the right side. The idea is super simple. You take an image from the internet and you take the text in caption for this image, and you assume that typically the caption of an image describes somehow what's in the image. And then what they did is they said, okay, we're going to learn an embedding such that the embedding vector for the image is similar to the embedding vector for the caption, which means they map text to the same vector that they would map an image. Okay, and by doing so on millions of images and captions, they can learn representations for both the text and the images that somehow contain semantic information. And it turns out that it works also extremely well on other tasks. Now, the problem with this representation from a robot manipulation perspective is that it's not fine-grained enough to allow you spatially accurate manipulation tasks. Okay, so this is where Mohit came up with the idea of combining these two networks into a single architecture, and they're hopefully then leveraging and taking advantage of both of these properties that these different kind of networks provide. Not going into the big details here, but the idea is here that we have as input is an image, top image of the scene. And this is a part that comes from the Clip network that I just described. So what it does is it takes, again, the top view image and generates an embedding vector that was trained on this very large ImageNet, or not ImageNet, internet data set. And also in our case, we give the scene together with, and then we have a decoder architecture that goes to a representation that tells us what the robot should do in this context. We also have an image input. So for example, the task might be pack all the blue and yellow boxes in the brown box. We again take the Clip network and generate the encoding that it has learned from internet data and combine it in the decoding of this vector. Again, details are a bit tricky here. And then we have another stream that is the transporter network. So again, the upper part is the Clip, the lower part is the transporter network. And by combining these, we hope to get actually the benefits of connecting transporter networks with language capabilities. And I'll just show you examples what we get from this now and kind of give you an idea of how this works. So imagine you want to train your robot to fold or unfold this towel here. Okay, and again, the tasks in this case, it's really the notion, we don't want to teach the robot to do like a huge variety of things, but we want to be able to teach it specific tasks, very specific tasks from a small number of examples. Okay, so if you think about the example here, fold the cloth in task, then the labels that we give to the system is in red, we say this is where the gripper should go before closing, which means one end of the towel. And then in green comes a place label with an orientation of the gripper as well that says this is where it should move and then release. Okay, and here are 9 examples that Mohit gave to the system. And this is actually done on the real robot. Yeah, and it took him 10 minutes. And that is the training data if you want to teach the system now to fold or unfold that piece of cloth. Here are other tasks. You trained the same network. For example, the stacking tasks, you might say the language description is put the blue block on the yellow block, and then the pick location for the gripper would be the blue block, and the drop location would be on top of the yellow block, for example, right? Or if you want to teach it, like, let's go take the example on the lower right here, there's a rope, and you say close the loop. Then the pick location would be one end of the rope and it would drop it on the other end of the rope. Okay, and then you get a loop. So, but as you can see here, actually the tasks that we specify here have a pretty strong variety. In total, we have only 179 examples. Okay, that's the only examples given to the system. And there's a single network that is trained on these. With transporter networks, this would not be possible. With transporter networks, you would have to train one network for every single task. Okay. One other thing I would like to highlight is that by using language, first of all, we help the network to disentangle the different tasks it should do, but also the network can learn, for example, the notion of blue, what it means for something to be a blue block. It could learn that in the context of the stacking task, but it can then use that in the put in the bold task, which means in the put in bold task, we might not have an example that involves the blue block, but hopefully it has learned what blue means in the stacking task. Okay, and we see some evidence for this actually happening. Now, let me show you examples of just like, again, what the robot can do now. Again, this is from 179 training examples.
Put the orange block on the blue block. Put the red blocks in the green bowl.
So in this case, it had never seen the task red block in green bowl, but because it's using language, it can transfer and combine different demonstrations it has seen with colors.
Pack the white tape in the brown box.
Have in mind that, again, these are all tasks that are doable in this top-down pick-and-place manner.
Box.
Also, another caveat, the language is still
in the brown box.
Somewhat scripted. We haven't done totally open-ended language in this context.
Pack the red whiteboard marker in the brown box.
Here, the next one you'll see is another nice example for this generalization that you would not get with transporter networks.
Pack the blue whiteboard marker in the brown box.
So it's never seen a blue whiteboard marker in the training, but it has seen a whiteboard marker, a red one.
Put the orange block on the blue block.
Oh, okay. So here's another example. On the upper left, you can see somewhat the representation that the network is using internally for these kind of tasks. Let me start this. Oh, wait, sorry. Where we have the pick location and the place location that the network identifies in these different scenes. So as you can see, it was trained to be invariant also to these light rotations and things like that. This is a task, again, that with pure object representations wouldn't make a lot of sense, right? Because it's really hard to reason about objects in this context. That is where this action-centric representation is very beneficial. I'll give you two more examples and then we're done. Again, just to show you the kind of variety of things you can do, and just simply by training the robot on, I don't know, it took him maybe 2 hours or something like that. Okay, the caveat is, one more I want to give, the training of the network actually takes, I think, significantly more than a single day, because the network uses these examples and applies many variations to them by rotating the images and everything, so that the network is trained to be equivariant or invariant to some of these changes. This is, I think, a very cool one, because to pick up these cherries, you don't want it to pick it up at the flesh, but actually at the stem. This requires actually pretty fine-grained visual recognition here. Okay, and that is something that with a pure clip-based network you could not achieve. It also learns to, let's say, kind of read. And again, we get this benefit through leveraging the clip networks, because clip networks were trained on this huge amount of internet data. So in this case, the training data was also given with a label of good and bad, but it was written in a different style. All right. Oh, this is, we did also many simulation runs on this. And here you can see the score we are getting by combining clip networks and the language with the transporter networks. We get a big boost. And interestingly also, this is the result we would get if we train a single network for each task. And this is the result if we train a single network for all the tasks combined. So actually the network doesn't get worse, it gets better, because it learns to leverage information across tasks, okay? And with that, before Dan gets too nervous, I'm getting to my last slide. We're kind of on time, I think. So just to very briefly summarize, so we've done a lot of work on manipulation with explicit object models. And there's clearly a lot of benefit to that. We can do very complex reasoning and planning with these systems. It's extremely general, and it clearly still has its place. So I'm not going to say anywhere that we should never use models, or in many industrial tasks, you might actually have very good models for things, and we should leverage these. But I think in many settings, going from raw observations, from the raw data, to some kind of representation that is not dependent on these explicit shape models can be very beneficial. And I believe actually almost counterintuitively for some people, it can be more robust than leveraging explicit shape models, I think. Okay, I think that's from my perspective, an important insight. All of this, a lot of this can be really trained in simulation nowadays, of course. Where does the data come from always is a big question. And I think with simulation getting better and better, we can leverage that. The key advantage of using simulation is, of course, that we have access to the ground truth state, and we can generate training data that is much better than, and labels than we could do in the real world. And then I gave these two recent directions on learning object-centric representations from raw data, using these embeddings and transformer network architectures, and then with Clipboard also leveraging these really large-scale data sets and the capabilities of the pre-trained models for fine-grained manipulation. And with that, of course, I want to thank all the great researchers in the lab, and we also had some amazing interns over the last years, including some also from, of course, GRASP, like Bernadette, maybe she's somewhere here on the participants. So I'd like to thank everybody, and I'm happy to answer some questions.
Peter, thank you so much for that wonderful, exciting talk. I have many questions, but I think what I would rather do is I would rather introduce our panelists and have them transduce questions from the audience. And then if there's any time at all, I'll chime in too. But I'd like to introduce to everyone Dr. Matt Kvalheim, who's on location. Matt's a postdoc in my group, and he'll be handling questions from that end. I'd also like to introduce Bibit Bianchini, who's a doctoral student working with Michael Posa, and she'll be handling the online questions. So I'm going to just get out of the way right now and let the students talk to you, Dieter, and if there's any time before we have to leave, of course, I'd love to ask you some questions about this work. Okay, my suggestion, maybe Bibit and Matt, you might just alternate. Maybe that's probably the way to go. I'm going to get out of the way.
One quick question before we go there. Should I stop sharing, or what should I do on my side?
That's up to you.
I can just leave it like that. Maybe if there's a question for which I want to go back to a slide or so, we can just.
Yeah, you might want to leave the slides available just in case people want to look at them, and then we can leave them aside if no one's asking questions.
I can go ahead and get started with our first virtual question. So a question from Edward Hu is there a sense of how Clipboard is using the language for executing behavior? Is it treating the embedding as a bag of words, or is it actually using the ordering of the sentence? And
that's such a good question. So,
there's a follow-up as well. So would it be interesting to fine-tune the clip embeddings from the Clipboard model so the language embeddings become grounded in interaction as well?
Yes to everything. That's a great question, because the thing is, so the language, right? Like, does it do anything, actually use it? Does it really help us, or is it just coincidence that it works? It is not, it's not quite doing like fully semantic understanding, right? Especially the actions themselves, verbs and stuff like that, as you can imagine, is not well represented in the data Clip was trained on, because it's trained on just images with captions. So temporal aspects and things like that are not well trained on, but we've seen clear evidence that it does leverage the words and the language understanding, and it's not just a bag of words kind of model. So as evidence, for example, we did one test, it's not in the paper, where we did the following. I said, let's just take the sentences that actually kind of scripted that Mohit generated, and let's just scramble the words, which means we take a word and just replace it by a random other word. Okay, but let's do that consistently so that the network has any chance of going from demonstration to the execution. And it turns out that the accuracy and the capability significantly goes down, which means the network is actually taking advantage of the semantics that are underlying these words. For example, attributes like colors or object names and things like that is clearly being used by through the language part. And that's more tests we want to do. That's a great question. That's exactly where we want to go further and dig deeper into what are the things that are actually being revealed. And then that also going then to the second question, I'm absolutely sure that we will see many limitations where we're not fully leveraging the language, right? The semantics and the grounding of it. Can we train actually on many tasks such that we get better generalization and better grounding of this? And that's exactly one direction we want to look into. I think at this point, I must be honest, the generalization is still very limited, and we clearly want to go further with that.
Hello. With the work on learning object representations, it seems like a lot of the quality of the representation will depend on what the secondary networks are learning. Can you speak to how you chose which characteristics they should learn, and if you did any, like, if you have any intuition of what are good or bad things for those networks to learn?
Yeah, great question. You're referring especially to the logical predicates, right?
Yeah, exactly.
So we don't have any conclusive results on, let's say, alternatives. We're currently running. So for example, one question you might ask, what would they learn if we would train them explicitly on 60 poses and things like that, right? Again, the motivation from my perspective is we don't want to do this, but just for insight, it would be very interesting to see what we would get from that. Ultimately, we started this out actually by saying we just want to do contrastive learning, right? So this is somewhat still supervised learning we're doing here, even though the supervision is relatively weak, but you could even be weaker and do contrastive learning. The question is, from my perspective, how to best do contrastive training on this. For example, what are the kind of modifications you should apply to your images so that it actually learns useful things for manipulation settings, right? I think the standard kind of contrastive pre-trained networks don't really work well on these tasks. They don't have the kind of information that we need for manipulation tasks, I think. And the interesting question is, if you do contrastive learning, the question is always, what are the positive and negative examples? I know there's work out there that only works on positive, but what makes two scenes be the same? So what are even positive examples for scenes, right? If you have multiple objects in the scenes and multiple tasks the robot should execute, then it's not clear what it means for two things to be the same. Should two scenes be the same if in both scenes the blue block is on the green block, or should they be the same if the yellow block is in the gripper? So there is, if we go to these more structured complex settings, I think it's very difficult to come up with a clear notion of what it means to be the same or not, which is at the fundamental question you need to answer for contrastive training. But this is exactly also what we're looking at. Does that kind of address your question?
Yes, thank you very much.
But I think, again, coming from this, also from a robotics perspective, this is exactly where I think we need to go, right? We need to investigate these problems in a more robotics relevant setting rather than only in, let's say, internet images or things like that.
I will relay our next question from Rujna Bagchi. And her question is, what is the message to the students? And is the message that they don't need to learn physics, but that they need to leverage data science?
Yeah, that's a great question, Rujna. Thanks for asking. I believe that to do very good research in robotics with deep learning, you still need to know the fundamentals of robotics, being estimation, being control, so that on the one hand side, you can leverage these insights in developing your deep learning techniques, for example. Let's assume in the worst case, from Rujna's perspective, maybe you only want to do deep learning, right, in robotics, and you don't care about anything else. I think even then, if you want to do good research, you need to know, you need to have the background of what it means to do these things, for example, maybe in a more structured way, model-based way, because I think it helps you to ask the right kind of questions. And also, we need to train these systems, right? And where does the training data come from? What should it look like? And I think a lot of that is still very much informed by, let's say, model-based understanding and reasoning. So yes, please still learn the things. And of course, you can incorporate, it's not an either or. You can incorporate these techniques and insights into deep learning frameworks, right? From my perspective, deep learning is all about just making things differentiable. And if you make things differentiable, you can plug in any kind of algorithms and put them together and learn them end to end. It's not end-to-end deep networks. You can also have model-based components in them if you make them, for example, differentiable.
Mac, while I'm here, I'd like to ask a question. I'm curious whether some of the same techniques used to leverage semantic information in Clipboard could be used for non-object manipulation tasks. So suppose I want to tell the network, send an email to the boss telling him I'll be late for work. That's a very different kind of task. Do you have any ideas about that?
Yeah. So there's these two streams, right? There's the clip idea and then the transporter network. I mean, the limitation is that currently the transporter and the clipboard it's very constrained to the settings where you, first of all, it's kind of 2D. Okay, top view, top down manipulation with a rotation. So it's like 2.5D or 3D, depending on how you want to see it. And the task in this case is very much driven still by, it's all visual in the scene, right? So there's currently no real longer term planning about things that you can't see right now, right? So for example, even within a kitchen, if you want to say set the table, you need to reason about where are the plates, where are the forks. You need to go to the cabinets and they might be closed. So these things are currently difficult or not possible to represent in, for example, transporter networks. But I think the notion of these clip networks and the strong language understanding and visual understanding, I hope can also be leveraged in these tasks as well, because it gives you a much better understanding of these scenes right away. But it's not like an easy extension, right? And this is one of the tricks we see over and over again in robotics, that going from 2D to 3D and more complex settings is not just a question sometimes of, oh, well, I'll just generate twice the amount of data and it's going to work. It often requires kind of a real jump in the capabilities and in the reasoning.
Looks like we have only time for one more question according to our management. So Vibit, I guess you get to choose which of the several questions you want to prefer to our guest, and then I'll give a closing thanks.
Sure, I will relay the last question from Arjun Guru, who asks, is it possible to train object-centric representations on compositional representations of the environment, like scene graphs, instead of logical predicates representing the relationship between just two objects at most?
Yeah, that's a great question. I think there's actually two things I think that might be interesting here is, for example, you could see the way the sonnets operate, these embeddings. I can view this also as you can just feed these embeddings themselves during training into another transformer or a graph network, right? They can become the nodes in a graph network, and then you could train all of this jointly. Now you could say this could be graph networks, but even that level could be another level of transformer networks. So I kind of view transformers, graph networks are kind of, I know some people might hate this, but graph networks are a special kind of transformer networks, right? Where transformers can just learn the connectivity. They're just fully connected. But so in that sense, I think this is just the beginning, and you can now feed this into higher level reasoning that goes beyond pairwise objects. Also, I think these embeddings, I don't think they are constrained to rigid objects, right? So for example, when we saw some of these tasks where it's about granular media and things like that, or deformable objects, it might be interesting to see, can we learn just the same kinds of embeddings for deformable objects, right? And I don't see a conceptual reasoning why that should not be possible.